Now we have seen the various types of photodetectors. Okay, then we have seen the characteristics of photodetectors also. So which characteristics we have seen? We have seen the sensitivity, correct? Then we have seen the fidelity, right? Then we have seen the quantum efficiency, right? Then another characteristics, that is responsivity, right? Then again we have the noise characteristics. We have the minimum noise. Then we can see we can have the stability performance. Then we know the receivers should have the small size. It should have the low cost. It should require a low bias voltage. So this should be the characteristics. So I will note it down here. So stable, your detector should be stable. Then it will have the small size. You can note it down. Then it will have the low cost. So this should be the characteristics of your detector, and it should be highly reliable. Okay. So these characteristics we have discussed. Okay. So out of this, we'll focus on some of the characteristics. Okay. So please give the heading general characteristics of photodetectors. So I will give you the heading here. General characteristics of photodetectors. Now, while discussing this characteristics, I request all of you to please concentrate more on this. Okay, if you understand this, then you will understand anything. Okay, so now we know where the detectors are used, where the sources are used in fiber optic communication system. That we have seen earlier. Where the sources are used and where the detectors are used. Okay, so we are now focusing on the photo detectors. Okay, we are focusing on the general characteristics of photo detectors. So first characteristics we'll discuss on is quantum efficiency here in detail. Okay, so we'll represent it as eta. Okay, so this is quantum efficiency. Okay, then next parameter we'll discuss on is this is R. You draw the R somewhat like this. Okay, so this is responsivity. This indicate the responsivity here. Responsivity. Okay. Then we have the TR, small t subscript small r, small t subscript small r. It is, you can say, the rise time, or you can say it is the impulse response. Okay. Then where this rise time or impulse response, this TR is used. What is the meaning of this rise time? So this will correspond to what? Please take a note of it. It is corresponding to bandwidth of detector. Okay. So bandwidth of detector, or you can say how fast the detector can respond. You can note it down. How fast the detector can respond. Okay. So this depends on this TR. Please take a note of it. Okay. Then we have P noise. So P noise indicate here the noise power. okay, or it is related to what? Dark current. Dark current. What do you mean by the dark current? Yes. So,
Amplitude is dependent on the incident signal level.
okay, or you can note it down. Uh, Dark current. I will write here the definition for the dark current. So it is nothing but the residual emission of electrons. It is the residual emission of electrons when light signal is absent. Please take a note of it. Okay. So these are the four important parameters we'll discuss. Okay. Now first we'll focus on the quantum efficiency. I think you have noted all these points. Have you noted this?
Yes, sir.
Okay. So let us move forward. So now we'll focus on now the quantum efficiency. Okay, so it is represented by the eta. So how it is defined? So you can note it down this definition. Okay, it is the ratio of carrier flux generated, okay, which contribute to the photocurrent, and incident photon flux. It is the ratio of what? Carrier flux generated which contribute to photocurrent and incident photon flux. So this is nothing but the quantum efficiency. So for your understanding, what I will take here, I will take here, suppose that this is the piece of semiconductor, okay, and suppose this is, suppose you can say key photon flux. This is photon flux. I represent it by the phi. Okay, then how this photon flux can be calculated? Yes, what is photon flux? Phi. It is number of photon incident per unit time. Na? What is phi? Yes, any question? So if phi is the photon flux, what I can say? If phi is number of photons incident per unit time. Okay, so it is equal to P optical, P of divided by HF. So this HF is energy of one photon. If you have any question, now what I have said, the quantum efficiency is the ratio of carrier flux generated which contribute to the photocurrent and the incident photon flux. It is the ratio of these two, carrier flux generated which contribute to the photocurrent and incident photon flux. Now here phi is the incident photon flux I am taking. So how to calculate means how to have this phi? This phi is equal to what? P opt divided by the HF. HF is the energy of one photon, or you can say how to have this phi. This is nothing but the number of photons incident per unit time. Correct? Now, how I can write this? How I can write this eta? Yes. So carrier flux, how I can write? Yes. It is nothing but the IP by E. Correct? Is it correct? And how this flux phi is written, as I have shown here, it is P opt by HF. Okay, so this will corresponding to the carrier flux. and this will corresponding to the your incident photon flux, correct? So IP by E will indicate the carrier flux, and P opt by HF it will indicate the incident photon flux. So this is in the form incident output power and photo current generated. Okay, so this will corresponding to what? Incident output power. Okay, or you can say this is corresponding to the incident output power, and this will corresponding to the photo current generated. Okay, now here on which factors this eta depends? What does this eta depends on? Yes. So why I am discussing this quantum efficiency here? Please remember कि all the electron hole pairs that are generated need not contribute to the photocurrent, okay, in the external circuit. Please take a note of it. So if suppose I take here, so this is suppose my semiconductor, or you can say this is semiconductor photodetector. This is photodetector, okay, and suppose this is the external circuitry, and suppose this IP is the reverse current, okay, and this is the incident photon flux. Okay, so what I mean to say here is कि if photon flux is falling on this photodetector, okay, so definitely it will generate the electron hole pair. Okay, all the electron hole pairs that are generated need not here contribute to the photocurrent in the external circuit, or you can say need not contribute to this IP. Correct? We know, as we have studied earlier or we have discussed earlier, what we know, every incident photon will generate one electron hole pair. Okay, you can remember somewhat like this: one incident photon will corresponding to one electron, or you can say one EH pair, electron hole pair. So this is the case of suppose say linear optics, you can say. So here please take a note of it कि this eta, it is in the range of 0 less than or equal to eta less than or equal to 1. The value of eta, that is quantum efficiency, is lies between 0 and 1. Okay, so why we are focusing on this quantum efficiency? Because we are discussing the detector. Okay, and in detector we know कि we are using here, suppose for example semiconductor detector, and we know कि photons are falling on this photodetector, and this photon flux will result in the increase or decrease in the this reverse current IP. Okay, so we want to know in detail कि is all the photons incident on this detector will result or will contribute to the photocurrent or not? Yes, definitely it will not contribute. All the photons that are incident on the photodetector may not contribute to the photocurrent. Why they will not contribute? See, for example, if suppose I say कि suppose these photons as shown over here, if suppose they are incident on this photodetector, so this is semiconductor photodetector, correct? When they will incident over here, what will happen? So I will take here somewhat like this. So this is valence band and this is conduction band level. Okay, now so this after falling, what will happen? This electron will move over here. Okay, and here hole will be generated, and this is electron. Okay, now after falling of the photon of energy HF. Okay, now electron hole pair will be generated here. Now what will happen if this electron hole pair, you cannot say कि this electron hole pairs will not recombine. If what I have said कि one incident photon will result in one electron hole pair. Okay, so what will happen if this electron hole pair will recombine again due to you can say the defects in the material, or due to any reason, okay, if they will recombine, electron hole pair will recombine, then what will happen? They will not contribute this to this photocurrent IP. So meaning to say is, why this definition is somewhat like this, it is the carrier flux generated which contribute to the photocurrent. So this is very, very important, which contribute to the photocurrent. Okay. So this carrier flux, or you can say this incident photon will generate the electron hole pair, but generated electron hole pair can be recombined. Okay. So therefore all the electron hole pairs will not recombine. Definitely most of the electron hole pairs will contribute to the this photocurrent IP, but some of them will recombine. Okay. So therefore the definition of quantum efficiency is written somewhat like this, right? Now here you can say here, what you can say here, ki here motion of electron and holes inside the semiconductor is equivalent to what? Is equivalent to one charge E moving in the external circuit. Okay. So that's why I have written is IP by E. Okay. What is this E? This E results from this motion of, so here you can write motion of electron hole pair inside the semiconductor is equivalent to one charge E. Okay, one charge E moving in the circuit. Moving in the circuit. Please note it down. So I think you have noted this. Now our next aim is to maximize the quantum efficiency eta. Okay. Why we need to maximize eta? When the carrier flux generated which contribute to the photocurrent, if it increases as compared to incident photon flux, definitely this eta will increase, and we know the value of this eta, it lies between 0 and 1. So we need to maximize this quantum efficiency eta. Okay. I hope you have got the idea about this quantum efficiency. In detail we'll discuss. Okay. Now after this we have the responsivity. Okay. Do you have any question? You can ask. Okay. So we'll move forward if you have noted this. So next point we'll discuss on is responsivity. Responsivity. So in case of LED, how we can write the responsivity? So this is written by this R somewhat like this. Okay, you can draw in the Roman. So it is equal to P optical divided by I. So it is given in watt per ampere. Okay, so it means what? When you pass the current I, what is the optical power P of generated? Okay, so this is nothing but the responsivity related to, you can say, source, or you can say LED. Okay, so this is the responsivity of LED. So how to write the responsivity of LED? P opt divided by I means when you, because we know ki current will drive the LED na. current will drive the LED. Suppose this is the LED. So this current will drive this LED. Okay, current will drive this LED. So therefore P opt divided by I. So when you pass the current, what is the output power generated? Okay, so that is nothing but the responsibility of source or LED. Now we are discussing about the responsibility of detector. So how to have the responsibility in case of detector? Yes, R detector. How I can write the R detector? Yes, simply it is IP by P opt. Correct? Means it means what? Corresponding to the optical power, means power of incident photon, you can say optical power, how much current is generated. So it is in ampere per watts. And please remember this value R is equal to, suppose say 0.5 in case of silicon photodetector, it is in ampere per watt. So in case of silicon photodetector, okay, this value is 0.5. Okay, so you can write the definition of responsivity in case of source and in case of detector. Okay, so if you are writing in case of source, it is in watt per ampere, and if you are writing in case of detector, it is in ampere per watt. Because at the output what you are getting, what you are getting is written on the numerator. In case of detector, at the output you are getting the amperes current, so ampere per watt. And in case of source, you are getting the power output, so therefore watt per ampere. So please take a note of it. Okay, so this is required for the design engineer. So if you are want to design the electronic circuit, some design engineer wants to design the electronic circuit, so that engineer must know the what will be the output current generated in case of detector. Correct? Correct? Is that correct? Yes. So according to the need or according to the application, if you want some milliwatt of power or microwatt of power, or you can say depending on the application, he can generate the power, and accordingly he can design the circuit. Okay, so now how I can write this R responsibility R? Okay, so R is equal to, I have written IP by P opt. Okay, so now how I can write it? Because initially I have written ki eta is equal to what? Eta is equal to IP by E divided by P opt by HF. Okay, so it is the ratio of carrier flux and photon flux. So this is the ratio of carrier flux and photon flux. Right? Now how I can write this responsibility R in terms of this eta? Because you can see IP by P opt is there. Now if I move this divided by E and this divided by HF to the left side, so what will I get here? Yes. So in place of IP by P opt, what I can write? It is equal to eta into, yes, eta into E, right, divided by HF, right? So this is H, okay, and this is eta. This is eta. Correct? Now, can I replace F? Lambda is equal to C by F, I know. So can I write here? It is equal to eta into lambda divided by, I can write here H into C. Correct? Now we know how to have this. We have found out this ratio. Yes, C by lambda. Yes, C. What is just C here? If you put the lambda in micrometer, so what I will get here? So eta into lambda in micrometer. So I will get it is equal to 1.24, right? I have found out this. We have found out this, correct? So meaning to say here is कि for your application, depending on application, this lambda will be constant. Okay. So this responsivity of your detector is directly dependent on what? It is dependent on your quantum efficiency eta, correct? So this responsivity R is dependent on eta. Please take a note of it. If you have any question, you can ask. Have you noted this?
Yes, sir.
Now, moving forward, now I think you have noted all this, and you know you have now get the brief idea about the quantum efficiency and responsivity. Okay. Now, moving forward, we'll go more details on these terms because these are very important. So please concentrate now more. Okay. Thank you for your patience. Now, our questions are now on which factors this eta or quantum efficiency, you can say, physically depends. Okay, this is the first question we have. Then second question, how to maximize how to maximize eta. Yes, yes, can anybody tell how to maximize eta? So for this, let us go into the some more details here. Now please concentrate now. Now this is again the semiconductor photodetector I am taking. Okay, very simple. If you concentrate, you will understand. So this is the photo detector, specifically semiconductor type. Okay. Now here suppose the thickness here is D. D is the thickness. Okay. Now this is the incident photon flux on this semiconductor detector. This is suppose phi. Okay. Now, and this is suppose the depth direction like this x. This is nothing but the depth direction. Correct. Now here suppose I consider कि at the surface suppose Ri is your 1.0 means 1 and inside suppose 3.5. Okay. So now why I have shown here the two different refractive indices here, because we know if there is a change in the refractive index, what will happen? There is a reflection. Okay. Now here I will draw somewhat like this. So here I am taking the photon flux phi and here this direction x. Okay. Now here photon is incidenting on the surface, photon flux phi. Now here I will define here the new term, that is R. This is the capital R. Okay. Initially don't confuse with this R and this R. This is the responsivity. This is the Roman. Okay. And this is I have written capital R. Okay. So this is reflectivity. This is reflectivity of the material suppose. Okay. Now suppose I consider this R as the reflectivity, then how much flux will be reflected back? Okay. What I have considered here is this flux phi is incident on this photodetector, semiconductor type photodetector. then what will be my reflectivity? Yes, how much flux will be reflected back if there is a change in the refractive index, that is I have shown here, for example 1 and 3.5. So definitely if R is the reflectivity, then R into phi will be reflected back, right? Right? So if you find in case of laser, so I will give you brief idea about the reflectivity. So when you explain the laser, I have given explanation in the your homework also. So in laser, if you find this R, that is reflectivity, the value is somewhat is equal to R is equal to this R is equal to suppose say 0.3. Okay, 0.3. What it means? It means that 30% of the incident flux is reflected, okay, and 70% is incident. Okay, so this is the meaning. Okay, means if you are given the reflectivity of some material, it is equal to suppose say 0.3. So it means 30% of the incident flux or incident photon flux is reflected and 70% is incident. Okay, now out of this 70% incident on this detector, so this will create the electron hole pair. Okay, so out of the created electron hole pairs, all the electron hole pairs will not contribute to the photocurrent. Okay, because why? Because some of the electron hole pairs may recombine. Okay, please take a note of it. Now for this purpose, so to understand in more depth, uh, we are focusing on this photodetector as shown over here. It is semiconductor type, having the thickness D. Okay, now here I have considered the photon is incident on the this surface of this photodetector, and X is the depth direction I have taken. Now what will happen if R is the reflectivity? The R phi will be reflected back. Okay, the flux R phi will be reflected back. So what I can say here, ki in this diagram, suppose inside the material, how I can write the flux? Inside the material, I will not get the same flux phi. Incident flux is phi. Here incident flux is phi. Okay, but inside the material, what will be my photon flux? Yes. Yes. Here you'll get what? R is the reflectivity, na? So reflectivity again, it is in the range of what? Reflectivity 0 to 1, na? So therefore, I can say here how much power will be incident. Okay. So here I can take 1 minus R into phi, right? Is it correct? See why you are getting this reflectivity, because of the refractive index difference here. Refractive index difference on the surface and inside the material. So you will get the reflectivity, and due to this reflectivity, if phi is my photon flux, 1 minus R into phi, okay, will be inside the material. This flux will be inside the material, and this flux phi will decrease exponentially somewhat like this, like this. So here somewhat this distance, if I will take this distance is d. Okay, so therefore now now here flux phi is incident on the material, and inside the material you are getting 1 minus R into phi. Okay, R is the reflectivity. Okay, now to understand in more depth, again let us have, suppose, are you getting this point? So to understand this, suppose I consider the semiconductor material with the absorption coefficient alpha. Okay, So this is the piece of semiconductor material with the absorption coefficient alpha. Okay. Now if I consider I0 is the intensity of incident light. Okay, then, and what is I naught, or you can take how we can write now the output here. Okay, so suppose the absorption coefficient of your material is alpha and I0 is the intensity of incident light, then how to write the output? Output will be somewhat like this: I0 into e to the power minus alpha into d. Okay, so if d is the thickness here, like this, if d is the thickness, correct? So how we can write? So inside the material, how I can write this? So inside this medium or this material, how I can write intensity? So absorb intensity will be absorb equal to, it is equal to what? So incident is I0 minus output is I0 into e to the power minus alpha d. So I can write I0 e to the power minus alpha d. Okay. So it is equal to, you can write I0 in bracket 1 minus e to the power minus alpha d. Okay. So here I0 is the incident, na? I0 is incident. So this fraction is the absorb. This fraction is absorb. This fraction is nothing but the absorb one. Absorb intensity, you can say. Okay. So what I can say, कि difference between these two is nothing but the absorb in the material. Okay, and this absorb photon will generate the photocurrent. This absorb photon will generate the photocurrent, correct? So please focus on this fraction. Now here in this case, now you can see if phi is the photon flux, what is absorbed inside the material, phi into in bracket 1 minus r, as shown over here. Okay, now it will decrease exponentially, sorry, it will decrease exponentially. So here I can write e to the power minus alpha d. Suppose alpha is the absorption coefficient of this material. Okay, up till this d. Okay, after this, since the distance is x, depth direction is x, here you can take the constant. Okay, like this. Now if you have noted this, I will change the color here. Now why here the photon flux decreases exponentially here? Why photon flux is decreased exponentially here? I have shown here. See, alpha is the absorption coefficient, I0 is the intensity of incident light. Then you can get the output somewhat like this: I0 into e to the power minus alpha d. This is the way of writing. Okay, if alpha is the absorption coefficient, please take a note of it. Okay, now here in case of our detector, 1 minus r into phi, 1 minus r into phi, this will enter the detector material. This will enter the detector material, right? Is that right? Now this will enter the detector material. Now what will be the amount of absorbed photon here? Which amount of energy will be absorbed here? You can say 1 minus r into phi. This is the flux entering the material. Okay, how to write this? Yes. See, I have shown you here. See, this is the material, this is the absorption coefficient. Okay, if suppose input is I0 and absorption coefficient is alpha, input is I0, absorption coefficient is alpha, then what will be absorbed? I0 into e to the power minus alpha d na, or sorry, I0 into in bracket 1 minus e to the power minus alpha d, difference between these two, right? Difference between this output and input, this will be absorbed na in the inside the material. Now what I have said, ki 1 minus r into phi is entering the material. Now the picture is somewhat like this. So this is material. So here 1 minus r into phi is entering the material with absorption coefficient alpha. What is the output here? Yes. Simply you have to replace I0, I0. So in place of I0, what is there now? 1 minus r into phi na. So how I can write? 1 minus r into phi in bracket 1 minus e to the power minus alpha d. All other are the same na. Have you understood this? If you understood, please unmute and tell me you have understood. This is important concept. See, you are taking the detector material na. This is the detector material, semiconductor detector material. Photon flux phi is incident, right? Photon flux phi is incident on this semiconductor material. So what we have taken here, we know ki here the refractive index is suppose 1 at the boundary, and in the material refractive index is 3. Here is 1, here is 3. So due to change in the refractive index, what will happen? There exists a term reflectivity R. Okay. So all the photon flux that is incident on the material will not be absorbed due to this reflectivity or due to this change in the refractive index. Only the 1 minus r into 5 will be absorbed. So here 1 minus r into 5 will be absorbed. Then the absorption coefficient will be there. Okay. So since the absorption coefficient is there, how I can write the output? Output I can write in the same fashion. Input, suppose how I can write in this fashion. So output will be 1 minus r into phi into e to the power minus alpha d. So this will be the output I am getting, is alpha is the attenuation constant, absorption constant, correct? Then the amount of photon energy that is absorbed will be given by the difference between these two na, output by input, right? Sorry, input by output, input minus output, right? Have you understood this?
Yes, sir.
Okay. If you understood this, so now please note it down. I will give you 2 minutes to note it down. I think you have noted this. Let us move forward. Now, what we have considered, phi is the incident photon flux. Okay, then 1 minus r into phi. Okay, that is the flux entering the material. Okay, then we have considered what, phi into 1 minus r. Okay, this quantity into 1 minus e to the power minus alpha d. This is absorbed by the material. Okay, now this indicate this 1 minus r into 1 minus e to the power 1 minus r into 1 minus e to the power minus alpha d. This indicates what? This indicate the fractional number of photons absorbed. Fractional number of photons absorbed. Now, if I consider this is equal to zeta, if this is equal to zeta, so this is nothing but the fractional number of photons absorbed. Okay, so this will give rise to the two conditions, suppose, or it will depend on two conditions, or you can say suppose I consider ki n is the capital N is the number of photons absorbed. Okay, then we can say ki this zeta times n will contribute to the external circuit current. Okay, so zeta times n will contribute to external circuit current, right? Now, if I consider this zeta is the fractional number of photons absorbed, then we may have the two problems in our mind. So that two problems are key. Number one is, as I have discussed earlier, all the absorbed photons may not generate electron hole pair. This is the first condition or first problem in our mind. Okay, then all the absorbed photons may not generate the electron hole pair. This is the first problem. And second is, some electron hole pair generated may immediately recombine. Right? Okay, so this recombination is happened due to what? Yes, suppose this is the circuit. Okay, this is the circuit. This is your semiconductor detector. This is the photons, photon flux phi. This is the electron hole pair. Okay, and like this. This is your circuit. This is the external bias. Okay, so the electron will move from this side. Hole will move this side. Okay, you know this. Now they will recombine. This recombination will take place due to what? This recombination due to, you can say ki number one, you can consider due to you can say surface state, or as I have said, defect state. Okay, so this will happen, and due to this what will happen, this zeta will also contribute to the uh, uh, photocurrent generated in the external circuit, right? Because we know the two condition key all apps we know now. What we know here, phi is the incident photon flux, 1 minus r into phi. This flux is entering the material, and this is actually absorbed, phi into 1 minus r into 1 minus e to the power minus alpha d. This is actually absorbed. But after this, we come to know that all the absorbed photons may not generate the electron hole pairs. Okay, and then again, what you have observed is some electron hole pair generated may immediately recombine. Okay, so therefore, this factor phi, zeta, this will be added over here. So therefore, and we know that when the when this electron hole pair will contribute to this current, as long as they are moving, electron and hole pair, okay, as long as they are moving, they will contribute to the photocurrent. Now therefore I can say ki what will be the actual number of what is the definition of eta we have written? Yes, can anybody tell what is the definition of eta we have written? We have written carrier flux generated which contribute to the photocurrent divided by incident photon flux. Okay, so carrier flux generated which contribute to the photocurrent. This statement is very important to have the quantum efficiency. Now, so up till this we know ki how much flux is absorbed. Then we must know this fraction phi, zeta, so that we can know actually how much flux is contributing to the photocurrent. So therefore I can write here phi into or directly I can write 1 minus r into 1 minus e to the power minus alpha d into zeta. Okay, so this will be your quantum efficiency, because here phi is there and divided by incident photon flux phi is there. This phi get cancel. Okay, so therefore directly you will get this term. Okay, so I think our time is over.